So I thought long before I went to university that I wanted to do something in geology. You know, I'd collected fossils and I'd collected minerals, and I'd read about philosophy and a little bit about philosophy of science. And so I wanted to do something in geology, but I didn't really know what geologists did. And I didn't learn about it in my first year of university either. All I saw was a geologist standing in front of a lecture theater. But I was fortunate at the end of my first year at university, I got a job as an apprentice working for a real geologist who was making geological map of an area in the boreal forest and lakes of northwestern Ontario. And we were in the field for 4.5 months, a party of 4 people, the party chief who was making the maps and 3 students. And we didn't see anyone else except the pilot of a bush plane who came in once a week and dropped off some food, although we were usually out of camp when he came. And so 4.5 months we were in the northern Ontario bush making a geological map, which meant going out every day and walking through the forest. And whenever you see a rock that you were sure was part of the bedrock and not something the glaciers had moved, seeing what it was and identifying it and seeing how it was oriented and trying to put it into your developing picture of the structure and history of the area. Or other days you'd paddle a canoe along the lake shores, because there's a lot of excellent exposure along the lake shores. And so sort of outcrop, which is where a piece of bedrock is exposed, outcrop by outcrop, you'd build up this view of what's going on. And sometimes nature helps you out. So a lot of the times the rocks are actually, you can't see them because they're covered by lichen. But fortunately, there are clumps of moss which very, very slowly, increment by increment, millimeter by millimeter, they slide down the slope, and they go so slowly that the lichen where they are sitting dies because it's in the dark. And so it leaves behind it a streak where the rock is beautifully, exposed, and you can see exactly what it is because there's no lichen. So nature actually prepares the rock in advance for the geologist to come and investigate. But more seriously, many people think that geological mapping must be pretty routine work. I mean, you're just putting colors on a piece of paper representing different rocks. But actually, it's real science in real time. Because every time you go to, a rock outcrop like this and then figure out what it is and how it fits into your picture of the regional structure and its history, and once you've done that, then you look out there and you see all these other rocks that you could go to, but you don't have time to go to them all. And so you have to decide which ones you're going to go to. Okay? And of course, how you decide is that you make a prediction of what each of those rocks should be according to your understanding of the structure and the history. And so the one you need to go to is the one that would be most devastating for your understanding if it isn't what you predict it would be. And I would like to think that I have never gone to an outcrop without an expectation. Okay, so geological mapping is not routine. It is observation, synthesis, hypothesis, and test in real time on the time it takes you to walk from one rock to another. And you come back in the evening and you're physically tired, but mentally, you're just completely exhausted. As it happens, Kyoto stands at the junction of 4 tectonic plates: the Eurasian, North American, Pacific, and Philippine sea plates. All come together very close to here. This idea of plate tectonics, that there are large sectors of the Earth's surface that are in motion relative to each other, revolutionized earth sciences in the 1960s. In fact, precisely during the period at which I was at university, and as I jokingly said yesterday, if only we had known. And my work basically was to demonstrate that plate tectonics has been going on for billions of years. Okay. Now, here are two depictions of the motions of the plates. So to get you oriented, that's Africa and Eurasia, Australia, Antarctica, South America, North America, and then there's West Africa again. And the arrows indicate the direction of the plate motion, and the length of the arrow is proportional to the velocity. And the same map is shown on the lower panel, except that it is colored according to velocity. So the very bright colors are the plates that are moving rapidly, and the darker colors are the plates that are, they're just hanging around. They're not doing much at all. And what you see is that there's only a small number of the plates that are moving rapidly. The India-Australia plate, the Pacific plate, the Nazca plate, and the Cocos plate. And those are the plates that have trenches along a large fraction of their margin. And the motion of the plates is towards those trenches. And those trenches are places where the plate bends down and is actively sinking, is plunging back into the mantle from which it came. Okay? And only the oceanic plates can do that because they're negatively buoyant. They want to sink. The continents are like life jackets. They resist subduction, so they hang around at the surface. Now, I mentioned yesterday that one of the things I discovered from looking at plate tectonics from a perspective of billions of years is that the continents have undergone this stately dance where they all come together for a while, and then they break up and disperse, and then they come back together and again in a different location, different configuration. And this is, of course, a depiction of what is happening today. And when these cold slabs of oceanic skin or lithosphere sink down into the mantle because they're cold, they cool the ambient mantle. And as the ambient mantle cools from a long, history of sinking into a trench, what happens is that the ambient mantle itself starts to sink because it's been chilled and it's thermal contraction and what sinks. And of course, that means it has to, upwell somewhere else. And so you get this rolling action of things coming towards this sinking area, which in the world today is in the northeastern part of Eurasia. And that convection, along with the active sinking of the slabs, tends to draw all the continents towards that sinking area, just like leaves over a gutter. Okay? And so what this means is that the Pacific Ocean is the only ocean today that is closing. All the other oceans are opening. So in effect, all the continents are moving towards each other, and they're going to aggregate right here, East Asia. And so the next supercontinent, which I've called Amasia, will look something like this. Australia will actually arrive before the Americas. They'll have some protection. And we have a little over 200 million years with which to prepare. Now, plate tectonics is very old on Earth, okay? At least billions of years. Maybe goes right back to the beginning. But Earth is the only body in the solar system that has plate tectonics. It's possible that Venus had plate tectonics in the past, but it certainly doesn't have it today. Okay? So why is this? Well, the reason is that plate tectonics is very hard to start, but easy to maintain once you get it going. And the reason it's hard to start is because you have to tear that shell, okay, that hard, tough, cold shell. You have to tear it to get the sinking process started, okay? And I think that plate tectonics likely started very early in Earth history when the Earth was still very hot, the skin was thin, and it was being pelted by asteroids. I think that's likely when the tearing and the sinking of the oceanic plates began. But once it gets started, then the plate motions themselves, require areas where plates are diverging, that's the mid-ocean ridges, places where they're converging, where you have a lot of volcanic arcs. Those plate boundaries are maintained weak and thin, and so subduction can begin there. So it's a self-sustaining process. It's easy to keep it going once you get it started. So my prediction is, I mean, we don't have that many bodies in the solar system, so it's not, it's not that great a test, but we have a much larger, vast number of exoplanets. And we don't know yet how to tell whether an exoplanet has plate tectonics or not, but I'm hopeful that in the not too distant future, we'll figure out how to do that. And my prediction would be that plate tectonics will turn out to be rare, but long-lived where it occurs. Now, I was very fortunate as a field geologist interested in tectonics that my early part of my career coincided with a revolution in geochronology. That's dating rocks by radioactive decay. And I won't go into details, but there was a quantum leap in our ability to precisely and accurately date igneous rocks. Rocks that crystallize from a magma, using mainly this mineral zircon. And so the importance of that is that if you're making hypotheses or models about historical events, cause and effect relationships are easily tested with dating, okay? Because the cause must precede the effect. And in fact, anything that involves historical, working out things in a sequence, is most easily falsified by accurate dating. And dating also, governs the rates at which things happen, which is another, potential way of falsifying an idea. So this revolution in geochronology really converted a lot of what I was doing from competitive draftsmanship into real science, which means falsifying hypotheses. And as it happens, if you take all the tens of thousands of igneous rocks that have been dated, both directly and from grains of sand in modern rivers and ancient rivers, and you plot them all on a histogram from 4.5 billion years, the beginning of the Earth, to the present, and do their frequency according to the age of that zircon crystal, which you can date each of those grains, you have these 4 peaks. And zircon is mostly a minor constituent of granitic rocks. And granitic rocks form most of all when continents collide. And the crust thickens, and then thermal relaxation causes melting, and you get large granitic bodies. And so these peaks correspond to the 4 supercontinents that have occurred in the last 3 billion years, and Amasia is projected to be the next one. Okay, so as I was nearing 50 years old, I was looking for something to do after plate tectonics. And I met this guy, Joe Kirschvink, who was an old friend of mine, a paleomagnetist from Caltech. And he told me about this idea that he named Snowball Earth. And really the key thing was it was a self-reversing Snowball Earth. Now, he didn't actually develop the theory. That had already been developed, but he was the first one who thought it had an application to geology, that this event might have actually happened. It was developed in climate science as a theoretical possibility, but assumed to have never occurred. Okay, now the key thing is that sea ice, which can either grow or shrink, creates a positive feedback that amplifies any climate change, okay? In other words, if there's a cooling, the sea ice response, which is more sea ice, amplifies the cooling, makes it colder in addition to the original cooling. And the same in reverse. If it's warming, you get less ice, so there's an additional warming. And the reason for this is that in the summertime in the polar regions, so lots of sun coming down, most of the solar energy that would be absorbed by water is reflected by the ice, okay, and lost. If it falls in the water, it's absorbed, warms the water warms the air. hits ice, it's reflected and gone, lost. Okay, so and in winter there's even a larger climate effect, because if you have sea ice, it prevents the air from being warmed by the water, because in the wintertime the air is much colder than the water. And you would have a real limitation on how cold the air could be if the water was exposed. But if it's covered by ice, you know, the air is a little bit warmed by the water by diffusion through the ice, but much, much less than it would be. So it's a very important feedback. And what climate models showed, you know, already in the late 1960s was that there's a tipping point at the size of the summer polar ice cap. And if it reaches that tipping point, then the feedback becomes self-sustaining. And then the growth of the ice is unstoppable. And it grows uncontrollably until it meets the other ice cap at the equator. And then the surface temperatures fall far below the freezing point everywhere. And the ice thickens, flows under its own weight, so it heals any opening that might develop. And so about 99% of the ocean would be plunged into perpetual darkness. That means primary food production would stop. Same might happen, although this is much less certain, at the warming end, that a very small polar ice cap is unstable. So the idea is that we can be in the climate we're in, which is this one. We could be in this one, which we were in, you know, 50 million years ago, and in much of when the late period of the dinosaurs, or we could be here, but you don't go smoothly from here to here. You go there abruptly and violently. Okay. Now, climate scientists first thought there would be no escape from this. Okay. There would be no way of reversing that because of the high reflectivity of the ice cover. And so therefore it could never have happened because you're here. And so they never thought about talking to a geologist. Because as it happened, the geologists for 90 years have been sitting on data that showed that this probably did happen. But they had all sorts of ways they didn't know how to deal with it. They had no idea there was a theory for it. And so it was a sad thing that the theory was there and the observations were there, but they were in different worlds because of lack of communication between climate, which was at that time, and still to a degree, is a branch of physics, and geology. Okay, you know, my passion is to bring these fields together. So in fact, these three states, you can map that out on the history, climate history of the last 800 million years. Okay, so you can see that about 75% of the last 800 million years has been this state. And about 17% has been this state, the one we're in today. And these are the two snowball events. So here's the base of the Cambrian. The first animals, large animals, are about here. And then these are the two snowball Earth events that occurred in rapid succession. The first one lasted 55 million years. The second one, anywhere from 4 to 15 million years. Okay. Now, the beauty of the snowball Earth idea is that it's self-reversing. And that was first appreciated by a small group of planetary scientists at Ann Arbor, Michigan. And they realized that plate tectonics would continue. Okay, plate tectonics wouldn't care if the ocean had a kilometer of ice on it. However, the carbon dioxide that's emitted by volcanoes as a result of the geochemical cycling of carbon through plate tectonics, you couldn't get rid of that carbon dioxide because it's only soluble in liquid rain. It's not soluble in snow. And so the carbon dioxide that would be coming out of volcanoes would just accumulate. Okay. And slowly, the carbon dioxide would build up, build up, build up. And so if you came along and you got to that tipping point and you plunged into the snowball Earth, initially the tropical continents wouldn't be glaciated, but eventually they'd become glaciated too. That would be the very coldest period. And then, because of the accumulation of carbon dioxide over millions of years, the temperatures would rise. Okay, they would rise rapidly at first and then much more slowly later on, because you remember the temperature-CO2 relationship is a doubling. Okay, you have to double the carbon dioxide for every increment of warming. And when you have a lot of carbon dioxide, it takes a long time to double it. And so it's a logarithmic relationship. Now, eventually, either due to a combination of more and more greenhouse warming and a darker and darker equatorial surface because of the accumulation of dust on that surface, you reach the point where you first expose dark seawater at the equator. And of course, then you have the same feedback as working in reverse, because that dark water then absorbs energy, makes more water, which absorbs more energy, and then very rapidly, all the ice disappears, and you're left in a torrid aftermath in which you have a combined effects of intense CO2 greenhouse, but a dark energy-absorbing surface. Now, what is beautiful about this is that it makes predictions that can be tested with geological data, and that's what drew me to it, okay? I thought, this really deserves to be, we can test this, and if it occurred, the ramifications for the evolution of life are profound. And we really need to deal with this because what it tests is that the duration of the snowball should be very long-lived, millions to tens of millions of years. The onset and the termination should be very abrupt and globally synchronous. And the long snowball should be followed by the hottest climates and the highest CO2 the Earth has ever experienced. And all of those, each of those predictions has now been verified multiple times. Okay, here's a distribution of the cryogenic glacial deposits. This is the long older one and the shorter younger one. As you can see, they're really widespread on virtually all the continents except Antarctica, where you can't see very much. And it's been known actually for a long time. I mean, not as many deposit this, but the idea that there are no, but geologists said, oh, well, it's continental drift. You know, you put different continents through polar regions at different time. Don't worry, it's just like, you know, glaciation today. But I wasn't so sure. And one of the reasons is in many of these deposits, the glacial deposits are associated with carbonate rocks. And one of these regions is the area I decided to study. I spent 30 years doing field work here in the northern part, the African part of Namibia, along the dry, arid west coast of southern Africa. And there's this beautiful, thick carbonate succession, which has glacial, it has both of those glacial deposits. Certainly glacial, no question about it. And the importance of this is that carbonate forms preferentially in the warmest areas of the surface ocean. It's just basic carbonate saturation chemistry. That's why coral reefs are in the tropics. You know? So if you have glacial deposits at sea level in the warmest part of the surface ocean, where in addition there are no mountains from which glaciers could descend from frigid heights, that means colder areas must have been frozen as well. Right? So long before we had the dating or any of these other tests, I thought, look, this is not a normal climate. This is something radically different. Okay, so the response of life. Life was well evolved. So this is a time scale again, 3.5 billion to the present. And these are the cryogenian snowball Earths that I've studied. This is the one that Joe Kersfink has mostly studied. It's associated with the initial oxygenation of the atmosphere. And these snowball Earths occurred after life was well advanced. So we had bacteria, including cyanobacteria. You had many different eukaryotes, eukaryotic algae, including multicellular algae. We had protystin heterotrophs. We had fungi. You know, they had most of the constituents. We didn't yet have animals, although molecular clocks project the last common ancestor of animals to be in the cryogenian, but we don't. Well, we have actually organic chemical indicators of the first animals between those two snowball Earth events. And then land plants come later, although there are indications that a lot of the genetic toolkit for dealing with the difficulties of living on land actually may have been developed during the snowball Earth times. So the question is, you know, how did these organisms here, how did they survive if the oceans were completely dark and the surface was frozen everywhere? Okay, so here's what I think happened. And it's interesting because it's the same thing that's happening today, except in reverse. So deer flies, which bite your scalp, and so all field geologists know where the deer fly line is, have moved 1,000 kilometers northward in my career as a field geologist. in response to global warming. Right? So I think snowball Earth was just in the same thing in the opposite direction. Okay, so long before the snowball Earth times, there were mountains that projected above the snow line, like Mount Fuji. And this one here is right on the equator. This is Mount Chimborazo. It was made famous by Aimé Bonpland and Alexander von Humboldt, who studied the vegetation sequence here. And so long before snowball Earth, these glacial and periglacial habitats were colonized by microbial organisms. And when snowball Earth occurred, they just moved, with the ice sheets to the equator, because that's the zone of net sublimation on snowball Earth. And so they said, wow, this is great. Our habitat area is vastly enlarged, and the cruelty of winter is greatly reduced. Because we hardly recognize winter at the equator. Okay? And so those organisms that were pre-adapted, they flourished. And when the snowball came to an end, and the oceans rose because of the ice sheets melted, and warmed rapidly and were full of nutrients which were biologically vacant, the organisms had the choice either to go back to the mountaintops or to restock the oceans. I call this the Quito Express hypothesis. This is about the train that goes back and forth from Quito past the Chimborazo mountain down to the coastal city of Guayaquil on the Pacific, just about on the equator. Okay. Now, there are two ways of testing this idea, and the first is, do these polar alpine microbial ecosystems, do they have enough diversity to account for all the radiations of life that came after? Okay, and so here's where I'm greatly indebted to Japanese scientists who've been very prominent in the field of both Antarctic and Arctic ecology, microbial ecology, for a very long time. And so these are actually quite diverse ecosystems. So here are two. This is called cryoconite. All glaciers have an accumulation zone and ablation zone. The ablation zone is dark because it's got these holes called cryoconite holes, about 1/2 meter deep. In summer, they've got meltwater. In winter, they freeze up. And the meltwater is there even though the air temperature is below freezing, because there's a dark clump of dust at the bottom that absorbs solar energy and allows the melting. The dark color is mostly from heavily pigmented cyanobacteria. And because the cyanobacteria there, it's about 10% organic matter. There's a whole host of other organisms as well, protists and algae and fungi and even microinvertebrates. And so that's a freshwater environment, very bright light. This is another one. These are these ice-covered lakes in the dry valleys of Antarctica, and they're salt stratified. So the bottom waters are salty. They're isolated from the surface, so they get very warm. So they're warm, anoxic, nutrient-rich, and most of the productivity there. But the environment is almost exactly the opposite of this one, which is oxygenated and fresh water, but nutrient-starved. And so that actually explains why there are two classes of all green plants. There are the chlorophytes, which are mostly marine. There are the streptophytes, which are almost exclusively fresh water. And they have different photorespiration mechanisms. The chlorophytes, the ones that would be living in the dim light in those salt-stratified lakes, they have this old-fashioned photorespiration is a way phototrophs get rid of toxic byproducts of photosynthesis. It's an essential function for phototrophs. And chlorophytes have this old-fashioned mechanism that they inherited from cyanobacteria. It's very slow, but it's very energy efficient. So it's ideally suited for this, this dim light habitat under an ice cover in a lake, whereas streptophytes have a newly invented 3-organelle mechanism that is very fast, but it uses a lot of energy. But of course, if you're at the surface in that bright sunlight, you have a surplus of energy. Okay, so here's the bottom line. All living things descended from the survivors of snowball Earth. All right? And that was only a small subset of what had evolved up until that time. That means that earlier fossil record is additionally precious because we don't have those lineages anymore. They became extinct. But who we are derived from the survivors. Okay? And that tells us quite a bit. If that's true, that tells us a lot about, and should be testable in the genomes of living organisms, because the genomes encode, ancestry that can be mapped out on phylogenetic trees. Okay? But we have to convince biologists that this is worth doing, because it's deeply rooted in biology that life originated in the tropics, and cold environments are highly derived. And of course, but if you look at the history of life from the additional snowball perspective, the life we have could have had quite a different ancestry. I'm not saying it originated in cold water, but it lived in cold environments for a long time that allowed for its preferential survival. So it's been a great, I've had so much fun, unearthing these unlikely stories from Earth's own past and sharing those stories with others. I mean, that's just been a wonderful thing to have devoted my life to. So thank you very much for listening to my stories.